He's done. There's
I think I'm gonna go ahead and get started. I'm sure a lot of people gone today, but we're gonna record this as usual, so hopefully people will catch up on everything. Hope you guys are doing okay. It's been, I don't know, I have really watery eyes this morning. I don't know if it's the dust in the air and all the wind we've been dealing with. So I think I got a good night of sleep, but I sure my eyes would suggest that I didn't. But hopefully you guys are doing a little better than I am in that department. Let's see, a couple of quick announcements, and then we're going to jump in today. Don't forget that there's nothing due tonight, but we do have a homework assignment due tomorrow night. It's a fairly long one. I know a good number of people have already been getting a nice start on it. During the break, if you've got, or even right now, if you've got some questions that you'd like me to go over on the assignment, please feel free to jot them down and we will take a look at those a little bit later in the class. So that's coming up for tomorrow night. I will probably try to add some office hours tomorrow as well, since it's going to be due tomorrow. It makes sense. I'll try to be around. And then after that, of course, we have a long weekend. We have Monday off, which does me absolutely no good since all my classes are on Tuesdays and Thursdays. But maybe it'll be a little bit of chance to sleep in a little bit and get a little bit of extra rest for Veterans Day. Your next homework for this class will be due on Tuesday night, and it will be covering mostly about the stuff we're going to talk about today. So I think that'll be good, and I'll have my office hours on the weekend. I'll let you know all about that as well as we get a little bit closer to the weekend. But that's about all I got for right now. We're just a couple weeks out from our Thanksgiving break, and between now and then, it's mostly just going to be trying to chug through the homeworks and the material. Just so you know, we're only doing 9 chapters this semester, so we're already halfway through number 7. So we only have a couple more chapters to go after this one. So we're making good time. And next week we will definitely be going back to the differential equations again. So for those of you who have been waiting for very patiently for us to move on from the linear algebra, we're not too far away from that. And the best part of this class is always yet to come. It's always the stuff at the end, because that's when we put it all together, right? Everything we've been learning, all these skills and tools we've had, we're actually going to see it all coming back together in full circle by the time we get to the very end. So I'm excited about the month or so that we have ahead of us to kind of wrap up the material. So anybody have any questions about where we're at or anything with the schedule at this point, Audrey? Oh yeah, I know exactly when the next exam is. It's on not the Monday we come right back from Thanksgiving, but the following Monday. So, which is actually right before finals. I'm sorry, Tuesday. You know what? For years I taught classes only on Monday and Wednesday, and so for some reason in my head I got Monday in my head. Yes. So your next midterm is on, I believe that's Tuesday, December 10th. It's a week or so before the final exam. I generally do that because when you study for that third midterm, whether you realize it or not at the time, you're actually studying a lot for the final as well. So yeah, but all of that will be after Thanksgiving, and I promised myself I wouldn't give a midterm the very day we're coming back from the break. So but we'll have a whole nother week once we come back from the break.
Sounds good, thanks.
Yeah. So that's kind of where we're at. Yeah, so let's take a look here. I've kind of tried to recap the start of chapter 7. We got a little bit of time on Tuesday to talk about this, and I just want to kind of get this back in the front of our minds again. Chapter 7, we're talking about eigenvalues and eigenvectors. So this is always a pairing. They always come together as a pair. You'll have an eigenvalue and then a corresponding eigenvector. And the lambda is the notation for our eigenvalue. The corresponding eigenvector is V. And the relationship between the eigenvalue and eigenvector of a matrix, let me just remind you here, by the way, this matrix is always a square size matrix. Let's say n by n. The most important thing, the most important equation in chapter 7 is the one right here in this box, which is that A times V should equal lambda times V. So if I could draw a picture for you to remind you, we did this on Tuesday, but I just want to put it up here one more time. An eigenvector is a vector V such that after you multiply it by the matrix A, it doesn't change direction. It literally just gets stretched out by some scalar value of lambda. So AV is just the vector V with some stretch factor of lambda that's been applied to it. Okay, so AV equals lambda V. So that's the sort of the geometric interpretation of what an eigenvector is. It's a vector that just gets stretched by the matrix capital A. Of course, what we're going to want to be able to do is find these eigenvalues and eigenvectors for a matrix. This is going to be the key thing. And so I've got a couple of boxes here that are kind of intended to remind you how you do that. The eigenvalues are obtained by taking the determinant of A minus lambda I. Remember, this I is our good friend, the identity matrix with the ones going down the main diagonal. If we set that determinant equal to 0, we can solve for the lambda values. Those are the eigenvalues. Okay, so you'll be working with this. We call this the characteristic equation on Tuesday. I'll just remind you of that terminology. It's fairly standard. Characteristic equation right here. And that is the equation that allows us to solve for lambda. Once we have the lambda values in our hands, we can then go on to find the corresponding eigenvectors by calculating the null space of that same matrix, A minus lambda I. And because this matrix A minus lambda I is not invertible, notice it's not invertible because the determinant will be equal to 0. Because it's not invertible, that means that null space is not 0. Right? An invertible matrix always has a null space of 0. But if the matrix is not invertible, then there will always be vectors in this null space other than just 0. And those are your eigenvectors. Those are the eigenvectors. So essentially what you're going to be doing is calculating a lot of determinants and null spaces, right? To find your eigenvalues and eigenvectors. These null spaces are so special and so important in this theory that we actually call them eigenspaces. So the eigenspace of A corresponding to lambda, yeah, that's just this null space that I'm referring to in this box, okay? And we sometimes denote it with E sub lambda. Okay, and last thing I'll remind you about from Tuesday before we go on is just the importance of getting the eigenvalues right. Okay, if you get the lambda values wrong because somehow you solved the characteristic equation wrong, then you will be frustrated in your efforts to find the eigenvectors, and then of course then you can't find the eigenspaces, you can't do any of these problems. So it's really important to get the lambdas correct. And so I wanted to share with you some fun facts that really are not anything I can prove for you now, but I just want you to be aware of these. If you add up all of the lambdas, all of the eigenvalues of your matrix, they should add up to the trace of your matrix. The trace is just the sum of the main diagonal, right? And on the other hand, if I multiply all of my lambdas together, that the product of all of them should be equal to the determinant of the matrix. I like to just use these as a check. I don't really use these as a way of figuring out the lambdas, but once I think I've solved for those lambdas, I like to check them against those fun facts and just make sure that it's a reasonable list of eigenvalues that I've come up with. Okay, so we're going to practice all. We did an example on Tuesday, which was a 2x2 matrix. Today, I want to do some 3x3 matrices to talk a little bit further about this. But is everybody with me so far? Are there any questions about the recap or the summary that I've got up here on the board? So far, so good? Okay, fantastic. So let's try this this warm-up problem here, kind of practice everything. This is a typical problem that you'll be doing on next Tuesday's homework. It just says find bases for the eigenspaces of this 3x3 matrix. So this is capital A. And so let's go back and kind of go through the process. So for the solution to this, I'm going to first try to find the eigenvalues by writing down the characteristic equation. So let's start the solution right here. I'm going to take the determinant of the matrix A minus lambda I. What that means, guys, is that you're going to be subtracting lambda off of the main diagonal of the matrix. So I'm going to subtract lambda off of the main diagonal, like so. So subtract the lambda off of the main diagonal. Eventually, I'm going to set this equal to 0 and try to solve for lambda. Okay. Does anybody have a suggestion on evaluating this 3x3 determinant? How we might want to do it? Okay, we can look at this first column. Why do you notice the first column? There's quite a few zeros in the first column, and so what we can do, guys, is we can do cofactor expansion along that column. So I'm going to expand column 1 right now. So this is a little bit of a review of determinants again. So when you expand along this first column, right, you're going to take, what is it, the 2 minus lambda, right? And that gets multiplied by the determinant of this little 2x2 submatrix, right? Remember how the minors work? You cross off this row and this column, you do the determinant of this little 2x2. Let's get some big brackets here to help us write this down. 3 minus lambda times 3 minus lambda, and then minus 1. That part in the brackets is just your A times D minus B times C on this little 2x2 submatrix. And then the reason that Jason likes that first column, I think, is because the second and third terms are automatically 0 since the entries in the matrix there are 0. Okay? Everybody with me? This is the formula for the determinant of this matrix. Now, here's where we have to be careful. On Tuesday, when I had a 2x2 matrix, this equation was only a quadratic. And I'm not afraid of quadratics because I know that I have a quadratic formula. I could solve for the lambdas by using the quadratic formula. This, however, as you can see, if you were to multiply it all the way out, you would have a lambda times a lambda times a lambda. And that would actually end up giving you a cubic equation. And cubic equations are much more difficult to solve for the roots of unless you get lucky, right? Unless you have super nice numbers or whatever, you can get lucky. So we're actually going to want to be very careful here. Again, I keep talking about how important it is to get the lambdas correct. So we have to really focus on this step. I do not want to multiply it out. I do not want to do it. If I was to multiply it out, I would get a cubic equation whose solutions would be perhaps difficult to find. Instead, what I really want to do is get it factored. I want to get it totally factored. And I've already got this 2 minus lambda factored out in the front. So I don't even want to mess with that. I want to keep it out in front as a factored component of this product. Now, the part that's in the brackets, only the part in the brackets is only a quadratic. So if I'm going to use the same big brackets, again, guys, really try to use brackets and parentheses on this. I'm harping on this because this is the thing the students have the hardest time with. It's just getting the lambda values out of this thing. So the thing that's in the brackets, I do want to go ahead. I'm going to FOIL this one out. Lambda squared minus 6 lambda, and then plus 9 minus 1 is actually plus 8. And the reason that I'm okay with multiplying that part of it out is that that's only a quadratic. The part that's in those big brackets, I can factor that. I'm not afraid of that one. I can either use the quadratic formula if I don't see the roots immediately, or I can just see if I can figure out how to factor. This one actually factors very nicely. Namely, it's going to factor as lambda minus 2 times lambda minus 4. Okay. This is the way you want it, guys. This is the way you want it. You want those lambdas multiplied, or those factors multiplied together like such. And of course, what we're doing here now for this characteristic equation is we're setting that equal to 0. And so does everybody see then that I know what my lambda values are? I obviously have lambda equals 2, lambda equals 2, and lambda equals 4. Now, here's another very important thing. If the same lambda value is repeated, you should write it down as many times as it repeats. When you're listing your lambdas, right, so let's do that here. When you're listing your lambdas 2, 2, and 4, you should include repeats. The fun facts, for example, have the repeats baked in. So let's check these lambdas. If I add up my lambdas, I should get the trace of the matrix. What is the trace of this matrix? It's 8, right? 2 plus 3 plus 3, that's 8. So do these eigenvalues add up to 8? They sure do, but if I hadn't written down repeats, I'd get confused, right? So make sure you do write down repeats if they come up. The determinant of this matrix, let's see, if I expand the first column, I have a 2, and then the determinant of this little 2 by 2 would have been 9 minus 1, which is 8. 2 times 8 is 16. So if I multiply my lambdas together, I should get 16. So I like to check those fun facts, right? 2 plus 2 plus 4. Yep, that's equal to the trace. And 2 times 4, that's 16, and that is the determinant. So just checking those fun facts is never a bad idea. Okay, so that's that gives me some confidence that I have my eigenvalues correct. Everybody, so far so good? Now, for reasons that are going to become clear a little bit later today, whenever you have a repeated eigenvalue, and now we're going to go on and find eigenvectors, it's generally better to start with the eigenvalues that were repeated, if there are any repeats. Okay, so I'll explain more why we would care about that later. Technically, it says find bases for the eigenspaces. It doesn't tell you which eigenspace to do first and which one to do second and which one to do third or whatever. You can do them in any order that you want, but for reasons that will become clear in a little while, I would recommend always starting with any eigenvalue that actually was repeating. So in this case, lambda equals 2 was a repeat eigenvalue. Now, what am I going to do to find the corresponding eigenvectors? Well, I have to take the null space of the matrix that I get when I'm basically looking at this matrix, A minus 2i. 2i, lambda is 2. So I'm going to subtract 2 off of the main diagonal entries. So the 2 becomes a 0. So it's 0, -5, and 5. And then 0, 1, -1. And then 0, -1, and 1. So this would be the matrix that we would have. Now, another quick, is everybody with me on that? So I took the 2, the 3, and the 3 and knocked them down to 0, 1, and 1. I'm subtracting 2 off of the main diagonal, leaving everything else the same. Any numbers that are not on the main diagonal are literally just recopied exactly the same. Now, just another quick gut check here. This matrix has to be not invertible. Right? Remember that the determinant of this matrix is 0. So if we have any suspicions that we would get 3 pivots here, that would be a red flag. That would be something that would make me concerned that, oh, if the matrix is invertible, then I'm not going to have any eigenvectors. Oh, maybe I got my lambda wrong, right? That would be what I would maybe do, is go back and check. Is this lambda really correct? The fact that I see pretty quickly here, I think you guys can all see, this is not going to have 3 pivots. In fact, it's only going to have 1 pivot, because you can see that all of the rows are just multiples of each other. So I can cross off 2 of those rows immediately. Remember that you have unknowns when you're calculating these null spaces. I'll just associate the unknowns x, y, z with that. And the only equation that really needs to be considered here is the one in the middle, because the other 2 are just multiples of it. And what we see there is that y minus c is equal to 0. We circle my pivot right here. And so I see that C is free. I'll call it T. And based on that, I can solve for y, which is therefore also T. And this is a little bit weird, but the first column, it's all zeros, which just means the X doesn't show up anywhere. And that just means it's free. Right? The X is also free, so I'll call it R. I'll call that R. And so now, guys, I'm going to do what I always do, which is I'm going to bust out the variables and write down my basis. So the basis for the eigenspace E sub lambda equals 2 is going to consist of, okay, so I'm hoping everybody's feeling pretty good about busting out variables by now. When I bust out the R from these three values, I'll just get 1, 0, and 0. It's the first vector. And then the second one is I can bust out the T. And when I bust out the T, I get 0, 1, and 1. Okay, does that make sense? Yeah, Audrey?
And is there columns, because again, it's like the AX thing where it's a column of like unknown.
Yeah, it's good in this chapter to draw your vectors as columns. The back of the book might write them as rows. It wouldn't really be wrong to write them as rows, but it makes more sense to draw them as columns because, yeah, technically you're taking these vectors. Like, so let's just take an example. If we take the vector 1, 0, 0, right, that's an eigenvector, so it would be multiplied by A as a column. And by the way, if you do that here, you notice you end up getting 2, 0, 0. So there's a lambda factor of 2 right there. That's the eigenvalue. And yeah, so anyway, this would be your basis for this eigenvalue. Does that make sense? Let's look at the other eigenvalue. Let's look at the other eigenvalue. Let's do lambda equals 4. This time we'll have a slightly different null space. So we have to do the null space this time of, let's see what we get this time. The matrix when we subtract 4 from the main diagonal. So if I subtract 4 from the main diagonal, I'll have -2, -5, and 5. And then 0, -1, -1. And then 0, and -1, and -1. And again, what I'm most concerned about is to make sure that this matrix should be not invertible. I should not have 3 pivots here. And you can check it that the second and third rows are the same. So I can actually cross off the, guys, when I'm drawing lines through these rows, let me just be clear that like 8 weeks ago, I wouldn't have been doing that. I would have written down a twiddle. I would have said A2, 3 of -1. And then I would have had like 0, 0, 0. Cross off a row, what I'm basically doing is saying that I could zero it by using an ERO. And so you guys are welcome to do that. Right, back in September, I wanted everybody to show all their work and I make very clear that they know how to do EROs. We've been doing this for a while now. I'm totally cool with this, okay? And I'm going to circle these pivots. Again, they aren't technically pivots unless they're equal to 1. But again, we can be a little bit cautiously sloppy with it. I'm not trying to be sloppy on purpose. So anyway, I mean, if you really want to make this one a 1, it's not so hard. You can just change the minus signs to plus signs by multiplying the middle row by a minus sign. But let's write down the equations here. Y plus z equals 0. And -2x minus 5y plus 5z equals 0. Right. So in this case, I have only one free variable, which is t, which is z, and I'll call it t. So z is equal to t, which is a free variable. And then I have to back substitute and solve for y. So what is y going to be equal to?
-t.
-t. All right, perfect. So we'll put that up there. And then finally, I have to solve for x. This might take from the first equation. I'm going to try to solve this thing for x. So let's see. I'm going to just put the 2x by itself for a minute by moving it to the other side. -y, 5y plus 5z. Then I'm going to divide through by 2. Okay, so just doing a slight bit of algebra here. Divide through by 2. And now I'm going to put in -t for y. And I'm going to put in t for z. And I'm going to get something that's actually 5/2 t plus 5/2 t. Well, that's just 5t. So the x value comes out to 5t. I had to do a little bit of work for that. Let's just feed that in up here. 5t. Okay. So now I'm gonna bust out my variable and get my basis, right? So my basis for E sub lambda equals 4 would be the vector. So if I busted out the T, I would have 5, -1, and 1. 5, -1, and 1. Okay? So this is our warm-up example. If you're just coming in, you should get a picture of it before I erase it, and then maybe watch this video later because there's a lot of stuff I've been saying already. So I do start at 10 o'clock around here. I've said a lot of stuff already that is probably helpful for you to know. Any questions on this example? You might have noticed something, and I'm curious if you happen to notice this. Do you notice that our eigenvalues were 2, 2, and 4? And the eigenvalue that was repeated twice actually gave us 2 basis vectors, right? The other eigenvalue, which was at lambda equals 4, only showed up once, and it only gave me 1 eigenvector. So there's a 2-dimensional, so this is a 2-dimensional eigenspace. This one was a 1-dimensional eigenspace. And so your question might be, oh, does the dimension of the eigenspace always match the number of repeats of that eigenvalue? That would be a reasonable question to ask. Turns out that's not necessarily true. And so it just happens to be true on this example. But I'd like to do another example to show you that it does not have to be true. Everybody get what they need off of this board? All right, going. It'll be up on Canvas later. I'm always posting, remember, I'm posting these lectures online after the class in case anybody needs to pick up any of the extra notes. So let's try one more example. Okay, let's do another example. Find bases for the E spaces of, so let's take another matrix here. This time, I'm just to make it different from the first example, I'm going to use the letter E for this. So B is going to be the matrix 3, 0, 0, and then 0, 2, and -1, and then 1 and -1 and 2. So I'll call this matrix B for your notes. And so it's exactly the same question again, but I just want to run through it. So for the solution, we're going to just basically try to do the same process that we just practiced on the first example. I'm going to do that here as well. So we're going to take the determinant of the matrix that we get when we subtract lambda off of the main diagonal, right? So is everybody getting used to this idea? We subtract the lambda only off of the main diagonal. All of the other numbers stay exactly the same. Oh, this should be 2 minus lambda here. Sorry. Should look something like that. All right. So we subtract lambda only from the diagonal entries, not from anything else. To evaluate that determinant, does anybody have a suggestion? What would be the best way? Expanding the first row. I would agree with that. So let's do the expanding of the first row. Expand row 1. And that's because I see a lot of zeros in the first row. You might remember that you're technically allowed to expand any row or any column that you want. But it's always best to look for rows or columns that have a lot of zeros in them. So in this case, the first row has quite a few zeros. I only have to deal with this first term, which has a 3 minus lambda in front of it. And then when I cross off that row and column, I'll be looking at this 2 by 2 sub matrix. I'm going to use those big brackets again for the 2 by 2 that's underneath. So I would have a 2 minus lambda times a 2 minus lambda and then a -1. Remember that I do not want to multiply this all the way out. Because if you were to multiply it all the way out, you would get a cubic equation that would force you to find roots of an equation that might not be that easy to do. You actually would prefer to factor this, okay? You would prefer to get it factored. So that would mean try not to multiply it all the way out. Let's just keep the 3 minus lambda in front here. However, the part that's in the brackets, we do need to kind of simplify that. So I'm going to go ahead and multiply just the bracketed part out, and that's because this will only be a quadratic equation, right? So if I just do the part in brackets, I see a lambda squared minus 4 lambda, and then plus 4 minus 1 is really a plus 3. Okay, so I could write it like so. And again, my goal is not to multiply it all the way out. Instead, I would rather factor it. So 3 minus lambda, we'll leave that factored out. And then this is just a quadratic. This one also factors nicely as lambda minus 3 times lambda minus 1. And so if we set that equal to 0 now, we set that one equal to 0 this time. Now we get lambda equals 3, or lambda equals 3, or lambda equals 1. Those are my choices. Okay. So my lambda values here are 3, 3, and 1. Before I go any further, maybe I should just mention one other thing that I didn't say when I was doing the first example. When I was doing this determinant, you might have been thinking about using the arrow method. I mean, this is after all a 3x3 matrix, and so the arrow method is totally legal. The trouble with the arrow method, and the reason that you've seen me do 2 examples now using cofactor expansion instead, is that with the arrow method, you are going to have a harder time factoring. Because if you take like the first arrow would be this diagonal, right? Well, that's already 3 minus lambda, 2 minus lambda, and 2 minus lambda, right? So you'd have that already multiplied out, and then you'd have a bunch of other terms. I think there would be a minus 3 minus lambda over here as well. It's not that you can't do this. This is what you'd end up with. But you're more likely to just end up with a cubic equation all multiplied out if you do it this way. Instead of the cofactor expansion sort of helps you get it factored a little bit more directly. So that's why I didn't use the arrow method here. Okay. Let's check our fun facts real quick, guys. I want to make sure that these lambdas are correct. If I add up the lambdas, I get 7. Let's take a look at the trace of this matrix. If I add up the diagonal values, yep, that adds up to 7. So that's good. The other one is the product of the eigenvalues. So 3 times 3 times 1. What is the determinant of this matrix? If I expand row 1, I have a 3, and then that gets multiplied by the determinant of this little 2 by 2 square, which is also 3. So I would have 3 times 3, which is 9, and that is what this is equal to. So the fun facts seem to check out. Which of these eigenvalues would you recommend that I work with first? The lambda equals 3, right? This my comment from a few minutes ago is that if there's a repeated lambda, it's going to turn out to be better to start with that one. So I'm going to start with lambda equals 3 first. And because we're finding all of the eigenspaces. So there's one eigenspace for every eigenvalue, right? So in this case, there will be 2 eigenspaces. This is the first one, right? Corresponding to lambda equals 3. So I have to calculate the null space of the matrix that I get when I subtract 3 off of the main diagonal. So I'm going to go ahead and do that. I go back to the original matrix and I just subtract 3 from the main diagonal of the original matrix. So subtracting 3, I'll get the first row is all zeros, then I'll get 0, -1, -1, and then 1, -1, -1, something like that. Okay, and I'll just do one quick ERO here. I don't want to stress about it too much. I'm just going to leave the middle row. I'm going to move the row of all zeros to the bottom. The middle row, I'm going to do a sign change, and then I'm going to put the bottom row on the top. Okay, I'll circle my pivots like I always do. And of course, I've got my unknowns, which are X, Y, and Z. And as you can see here, the Z is free. There's no pivot in the third column, so the Z is free. Maybe I'll just put it right here, guys. I'll call it T. And if Z is equal to T, can somebody help me with what Y would be equal to? Negative T, right? Because Y plus Z. But so just to be clear, Y plus Z should be equal to 0. And also, x minus y minus z should also be equal to 0. So we would have that. So then if I want to solve for x, I just have to move the y and the z to the other side, which becomes y plus z, which is 0. So x is actually 0. So there you go. That's x, y, and z. And so now I can bust out my variable here and get my basis. So my basis for lambda equals, sorry, e sub lambda equals 3. My basis for e sub lambda equals 3 would be the vector. So if I bust the t out of this column here, I have a 0 for x, I would have a -1 and then a 1. And that's it. So that was my point. The eigenvalue repeated twice up here. On that first warm-up problem, the corresponding basis had 2 vectors in it. But look here, guys, this eigenvalue has failed to pull its weight. It has not pulled its weight. The lambda value of 3 has a weight of 2, but only produced 1 eigenvector. We're going to be trying to make a note of that as we go forward. This turns out to be a very important concept in the theory of eigenvalues. So this matrix B is somehow defective. I'm going to write down that word in the notes in a few minutes. It's a defective matrix. What I mean by that is not all of its eigenvalues are pulling their weight. Okay, so that's a good point. Now we do have another eigenvalue here, which is lambda equals 1. We do have another lambda value, which is lambda equals 1. Now see, here's the thing, guys. If an eigenvalue only shows up once, no repeats, then it will definitely pull its weight, because I know that I'm going to get at least 1 eigenvector. You have to. If you have an eigenvalue, there will always be an eigenvector to go with it. So eigenvalues that don't repeat will always manage to produce eigenvectors to go with them that is in the same abundance as the number of repeats. It's when you get these repeated lambdas, 3 and 3, and we only got 1 eigenvector here, that's an eigenvalue that did not pull its weight. And I generally want to know that information early in the process. That's the reason that I said it's nice to do the repeat eigenvalues first, because I want to get to issues like this, defective situations like this. I want to discover those early on. This one's not going to be a problem. We're not going to have a problem here. Let's just go ahead and do it. I'll do my null space again. I'm going to go a little faster this time. I have to subtract 1 from the main diagonal of the matrix. So I would have a 2, a 0, and a 0. The second row would be 0, 1, and -1. The third row would be 1, -1, and 1. Something like that. And, oh, okay. Another thing I should point out. Remember that this matrix cannot be invertible. I mean, unless we've made a mistake, right? As long as we've done this correctly, we know that the determinant of this matrix is 0 for that particular value of lambda. And that means that this matrix is not invertible. That means that if I took the time to do the EROs, I know that some row would have to get zeroed out. So you know what I'm going to do? I'm going to preempt all of that and say, yeah, I'm going to cross off this row. I don't even need to really do the EROs for that, because I know, see, I've already got 2 pivots here. Those rows are going to be perfectly good. But I know that if I was to go through all the motions of doing the elementary row operations, that I would have to get a row to get wiped out. And again, just to repeat myself from what I said a few minutes ago, whenever I just draw lines through these rows now, it just means I'm zeroing them out. I'm not being quite so, detailed in the EROs. I'm just saying, look, if I was to do the EROs, something's going to get wiped out. So let's wipe it out. All right, and that just makes your life so much easier when you're now trying to actually solve for this null space. So I'll set up my variables like so. Let's see, Z is free, right? There's no pivot in the third column, so I'll call it T. And then, let's see, that second row, that's just y minus c equals 0. So from that, I can solve for y. Y is equal to t as well. And then I'll take a look at the first row. The first row is just literally 2x equals 0. Right? 2x, 2 times x plus nothing equals 0. So x is 0. So x would be 0 here. And so now I'm going to bust out my variable. I'll get my basis. My basis for this eigenspace, this is lambda equals 1. Okay, I'll get my braces out and I'll bust out my t and I'll get 0, 1, and 1. Okay, be a little careful. It's not the same vector that we had over here where there was a minus sign in the middle entry. Okay, so altogether, this matrix only produced 2 eigenvectors, even though it was 3 by 3, right? Maybe you guys have started to notice a few things, like for example, because it's a 3 by 3 matrix, that's why we got 3 lambda values, right? It's because this is going to be a cubic characteristic equation if it's a 3 by 3 matrix. Cubic equations always have 3 roots. A 5th degree polynomial always has 5 roots. An 8th degree polynomial always has 8 roots. It's the fundamental theorem of algebra. I won't threaten you guys with this, but I always threaten my math majors with this, that if I go to the graduation and I'm sitting there and they're playing the music and you're about ready to go up, because I was usually the usher, so the students would have to like walk past me. I was like, there might be one last question just to make sure there was no mistake before you go get your diploma, which this is for the math majors, that they should know what the fundamental theorem of algebra says before they walk across the stage, and they're gonna have to walk past me to get there. So it basically is just, that's how important it is, right? It's just the statement that, you know, a polynomial of degree n should have exactly n roots. Nobody said that they would be nice roots. They could be, have horrible square roots in them, or they could be irrational numbers, or who knows what they could be, but they will always have 3 roots if it's a 3rd degree equation. Okay, so the number of lambdas is never in doubt. It's always just the size of the matrix. 3 by 3, we're going to get 3 lambdas. But what is in doubt is, will those lambdas hold their weight? Right? Here's an eigenvalue that repeated that did not pull its weight. Whereas on the first matrix we did a few minutes ago, every eigenvalue did pull its weight. I think it's time to write down this definition. I'm getting excited, and I want to make sure I get it into the notes for you here. So let me go back over here and write down that definition. Back on this side. Any questions though so far, guys? Yeah, Audrey, go ahead. Okay, so the thing about the crossing off of the row in that null space calculation, let me just clean up for a second here first. So you're bringing up a good point. What Audrey is asking about is over here, I'm starting to get a little bit sloppy. Oh, I'm just going to cross off a row. And the question that I think she's asking is, well, two things. First of all, why can I do that at all? It's because I do know that this matrix is not invertible, so that if I was to do EROs, I do have to get a row of zeros. If your matrix is invertible, you would have pivots going all the way down the diagonal. But if it's not invertible, which it's not because we set the determinant equal to 0, because the matrix is not invertible, I have to be able to get a row of zeros through the ERO process. Now, the second part of her question was an interesting one, which is, can you just pick any row? Can you just cross off, like, could I have crossed off the second row instead, or the first row? I happened to choose the third row just because it was the messiest one. I didn't want to deal with it. The first 2 rows were really nice because there's zeros in those rows that are easy to leverage. The answer is you cannot just cross off any row you want. I was going to bring this point up a little bit later, but you're asking it now. I'm going to answer it now. What if my matrix was like this? let's say this was, your A minus lambda I was this matrix right here. So in this case, I know that I have to be able to cross off a row. Yeah, let's just say we know that. But let's be careful. I would not want to cross off this row. Because the reason that I know that if I do EROs, something will get zeroed out, but you can already see that really it's the 222 row that I would probably zero out because it's a multiple of the first row. So you can't just blindly cross off a row, but here's how you can make sure you don't do it wrong, which is as long as the remaining rows that you did not cross off, this is for a 3x3. The remaining two rows, as long as they are not multiples of each other. Notice that the first two rows, the ones that I did not cross off, they are not multiples of each other. As long as those remaining rows are Li, then you did fine. Then it was okay what you crossed off. So maybe I should just make a note of that here. Let me come back over here and just put a little, I'm just gonna put a little asterisk on this. So just a little asterisk, we cross off a row since a determinant of A minus lambda I is equal to 0. And my point is that any row is okay. Any row can be crossed off. Any row can be crossed off as long as the remaining rows, whatever you did not cross off, the remaining rows should be Li. That's the answer to your question, Audrey.
And how do you do like, well, I guess just by looking at the two rows. But only one thing.
Oh, yeah, so that's another question is, yeah, you might have remembered on the first example, I actually crossed off two rows. Do you remember that? What was it? It was 0, 5, -5, and then 0, 1, -1, and 0, -1, 1 on our first example we did today. In this case, all three rows are multiples of each other, and I was actually able to cross off two of them. And in fact, that was the reason that we actually got two free variables on the first matrix that we started with today. And the two free variables led to this matrix having a basis of two eigenvectors for that eigenvalue. So on something like that, you just have to look at it and just see. Guys, obviously this stuff can get complicated if the matrix is really big. You're going to find out that my favorite size to have you work with is usually going to be 3x3. It's big enough that, you got to kind of know what's going on, but it's not so big that the calculations are crazy. So generally, I like to use 3x3 matrices. Yeah, Nathan?
If we had gone through like for that lambda equals 4, 1 and done all the rows,
Uh-huh.
I haven't done it in my head yet, but like could we potentially get a different basis?
You could definitely get a different basis. Any other basis that you would get would have to be a multiple of this factor. But yes, there's not necessarily, anytime you're being asked to find a basis for something, right? Anytime that's what the question is, you have to be open to the idea that there could be lots of right answers. Yeah, absolutely. Okay, so let me write down the definition. I've been throwing this word defective around a little bit. Just want to get into the notes now. This is a pretty important idea. The definition, an n by n matrix, capital A, with n linearly independent eigenvectors is called non-defective. Or there's another word that means exactly the same thing, so I'm going to write it down right now. Diagonalizable. Diagonalizable. So if the matrix has a full set of n linearly independent eigenvectors, we're going to call it a non-defective matrix. And the alternative word means the same thing, is diagonalizable. When I was a student learning this stuff, I saw both of these words used, and I got confused. I was like, what's the difference between diagonalizable and non-defective? Turns out there's no difference. Those words mean exactly the same thing. So just keep that in mind. Otherwise, A is defective. Otherwise, A is defective. So every matrix will either be defective or non-defective. And it just depends on whether the matrix has n linearly independent eigenvectors. So I'm going to rephrase this in a slightly more mathematical way, but to do that, I need a slight little bit of notation here. And the notation would be, I'm going to, so for an eigenvalue lambda, what I'm going to do, guys, is I'm going to let m sub lambda denote the multiplicity of lambda. M sub lambda is going to denote the multiplicity of lambda. When I talk about the multiplicity of lambda, that's just how many repeated times does it show up. So this would be, this is just simply the number of repeats of that lambda in the characteristic equation. In this characteristic equation, that's the number of repeats that you have there. It's the number of repeats. So like over here, m sub 3 would be 2, and m sub 1 would be 1. Just how many times did the eigenvalue repeat? So then here's my remark I wanted to make then, is basically if we take this matrix A, which is n by n, it is non-defective. Non-defective. Non-defective is a good thing, by the way. We want this. If and only if this matrix will be non-defective, if and only if, well, I've been saying it in words, so I'll write it in words first, and I'll give you the math behind it. Every eigenvalue lambda holds its weight. This is the way I like to phrase it casually when I'm talking about it. Every eigenvalue holds its weight. But now I can actually write this slightly more mathematically. Okay? Gerard? Yes, this one, so m sub lambda equals 3 would be 2. And this one would be the multiplicity of lambda equals 1, which would be 1. It's just how many times does that same lambda show up? And for each eigenvalue, you have this multiplicity number. Okay, so guys, the other way of just writing this now that's a little better from a mathematical point of view is just that the dimension of the eigenspace E sub lambda should be equal to the multiplicity of lambda, and this would be, guys, for each lambda, right? For each lambda. So every eigenvalue pulling its weight just means that if you look at its multiplicity and then you gather up the eigenvectors and you figure out what the basis is for those eigenvectors, that it should match up, right? That it should match up. So what I'm going to do, I think what would be good to do is to summarize with the two examples we just went through how this would all play out. So just for example, these are just from the examples above again. So remember that we had, the first one was the matrix A. So I'm just going to grab my notes out here and write them down again. This is just from earlier today, just recopying these notes. So from earlier today, we would have had the first matrix is this one right here. just kind of summarizing the problem again. On this first example, we had the lambda values of 2, 2, and 4. And in the case of E sub lambda equals 2, we came up with a basis of 1, 0, 0 and 0, 1, 1. And for the case of lambda equals 4, we came up with a basis. I'm just reminding you, we've already done all of this work just a few minutes ago. We came up with that eigenvector right there. So do you see that in this first example we did today, every eigenvalue pulled its weight. The dimension of the eigenspace matched the multiplicity of the eigenvalue. For this one, was that? For this one, was that? Make sense? So in this case, A is non-defective. By the way, it has to be every eigenvalue pulling its weight. If there's even one eigenvalue that does not pull its weight, then the matrix is defective. Okay, so now let's do side by side with that. I'll put down the second example that we just finished a moment ago, which was the matrix B. This was the matrix 3, 0, 0, 0, 2, negative 1, and 1, negative 1, 2. So I think this was the matrix B. And on this one, we got the lambda values of 1, 3, and 3. We still have some of the work on the board. For the lambda equals 1, we got the eigenspace for lambda equals 1. You can still see it over there. It was 0, 1, 1. Okay, and then for the lambda equals 3, we have an eigenvalue lambda equals 3. So this eigenspace, where do we have it? It's not that one. This is the first example. It's out of the way now. Where's my other? Oh, it's right there. It's right there, the stuff in blue on that middle board. That's my other eigenvalue. And so for that one, we got the basis of 0, negative 1, and 1, like so. And in this example then, for the matrix B, do you see the difference? Putting these side by side for you. In this case, the eigenvalue lambda equals 3 does not pull its weight. It has a multiplicity of 2, right? The eigenvalue repeats 2 times, only gave me 1 eigenvector. So B is defective. B is defective. So A is non-defective, but B is defective. So these are the 2 examples that we've done so far today, and you can kind of see a nice contrast between them. Do people understand this definition, defective versus non-defective? Pretty straightforward. Okay, let's do one more example before we take a break today, and then I think I'm going to feel pretty good about this little topic. Okay. By the way, at this point, you should still be asking, who cares? Oh, what's the big deal if the matrix is non-defective? What's so great about that? I'm going to show you that just a little bit later on today. Okay, but first, I just want to do one more example. Let's find bases for the eigenspaces of, this time I'm going to call the matrix C. And this one, this is only going to be a 2 by 2 matrix. So 2 and negative 13, and then 1 and 6. So let's try this example here. One more example to practice this idea again. So we're going to do the same process that we've been doing on these first 2. So I'll start my solution here again. Get this out of the way for a second. So I'm going to start by writing down the determinant again. The characteristic equation is the determinant of the matrix that I get when I subtract lambda off of the main diagonal. So it should look like 2 minus lambda, and then negative 13 and 1, and then 6 minus lambda. And again, when we're in the 2x2 scenario, everything is a whole lot easier because we know that this will be a quadratic equation, not a cubic equation. And so for this one, I don't mind if we just use the formula, AD minus BC. So this is going to be 2 minus lambda times 6 minus lambda, and then it's technically minus -13, but I'll write it as plus 13. Okay, and then of course I'm going to multiply that out. See here, I don't mind multiplying it out because it's only going to be a quadratic. So multiplying this one out is not going to hurt me at all. So what am I going to get out of that? Well, I'll get lambda squared, right? And then minus 2 lambda and minus 6 lambda is actually minus 8 lambda. And then I have a 2 times 6, which is 12, plus 13. So that comes out to plus 25. So here is my equation. We're going to be setting this equal to 0. Set equal to, I did give myself enough room there, write this out again. So this is lambda squared minus 8 lambda plus 25, and I'm going to set that equal to 0, like usual. And the thing with that equation, though, is that this one does not factor nicely. And this is why I'm doing this example. This does not have a nice factorization like the two that we did earlier. You could factor them very nicely. So what are we going to do if it doesn't factor nicely? Use the quadratic formula, okay? Don't be like those teacher credential students that I sit on the interview panel and I'll ask them, does that factor? And they'll just say no. And I'll be like, yes, it does. It just doesn't factor nicely. It still factors. So we can still find the roots of this equation by using the quadratic formula. So lambda equals, I just do, what is it, negative b, which would be 8 plus or minus the square root of b squared, which would be 64, minus 4 times 25 is 100, and then all divided by 2. So there's your lambda values, and let me just simplify those over here. 8 divided by 2 is, of course, 4, and so we'll have 4 plus or minus, ooh, look at that. Underneath the radical, I have a negative number. 64 minus 100 is negative 36. So what is the square root of negative 36? 6i. Is everybody familiar with our good friend, the imaginary number I? If you're feeling rusty on complex numbers, there's over the weekend, there is an appendix to this book that has a just basic review about, things like what is a conjugate of a complex number and, what is I squared? So I squared is -1. Just how do you sort of do basic math with complex numbers? If you need to look that up in Appendix A of the book over the weekend, this would not be a bad time to do it because we are going to start seeing complex numbers actually a fair amount between now and the end of the semester. So they will be coming up. Here's the first place that we're seeing them. The square root of negative 36 is 6i, but I have to divide that by 2. So once I cut that down by a factor of 2, it becomes 3i. Okay. Now, guys, before I go any further, can anybody already tell me whether this matrix would be defective or non-defective? So again, non-defective means every eigenvalue pulls its weight. Yes. Is it defective? Is that what you were going to say?
I'll just say this.
You were going to say it's non-defective. Okay, so we have a difference of opinion here. And I'm asking this question really early on, right? It seems to me, wouldn't I need to know the eigenspaces and all this stuff to figure this out? So why do you think it's non-defective so soon? Okay, these are two different lambdas. They are two different lambdas. There's no repeats here. There's no repeats. What got us in trouble with this matrix B was that lambda equals 3 repeated and then didn't pull its weight, right? But if the eigenvalues don't repeat, if you have just a bunch of different lambdas and there's nothing that shows up more than once, then we already know that C is non-defective. That is correct, since no lambdas are repeated. Of course, everybody has to understand that 4 plus 3i is not the same number as 4 minus 3i. Those are two different lambda values. There's no repeats. And if nobody repeats, then the multiplicities are all just 1. Right? Every single one of these m sub lambdas is just a 1. And so then the dimension of the eigenspace, of course, is going to be at least 1. I should actually make a quick comment here. I just realized I forgot to say this earlier. Some of you might be wondering, okay, let's say that there's an eigenvalue that didn't pull its weight. It came up short. Would it be possible for one of the other eigenvalues to overpull its weight to make up for that? Like, so you might be wondering, because at the end of the day, to be non-defective, I just have to have n linearly independent eigenvectors. So you might be wondering, well, if maybe the lambda equals 3 did not pull its weight, would it have been possible for the other eigenvalue to sort of overpull its weight so that you did have 3 things here? Turns out that can never happen. It can never happen. No eigenvalue can ever overpull its weight. And that's why when one of the eigenvalues falls short, it's already game over. The matrix is already defective for sure. So it's a good thing to realize. We will just need to know whether every eigenvalue pulls its weight. And if something doesn't pull its weight, the matrix is defective for sure. Okay. Anyway, here we have no repeats. So I already know that this is non-defective. Let's go ahead and continue. We're going to find these bases now. I'm going to start with 4 plus 3i. So we're going to have to live with these complex numbers a little bit. So I'm going to do a null space here. Okay, so now we got to be very careful. The math gets a little more tedious when there's imaginary numbers floating around. I have to subtract 4 plus 3i from the main diagonal of this matrix, right? So I'm going to subtract. So if I take 2 and I subtract 4 plus 3i, I'll get -2 minus 3i. And then I still have my -13 here. On the bottom row, I have a 1 here. And then I have 6, but I have to subtract 4 plus 3i. So that would be 6 minus 4 plus 3i is 2 minus 3i. Okay. Is everybody with me? So we have a matrix with imaginary numbers in it. We're supposed to find the null space. So, yes.
I'm sorry if you already said it, but so we can't really check for lambdas.
Oh, no, we can. Actually, we should do that. Thank you for reminding me. What is if we add up the lambdas, 4 plus 3i plus 4 minus 3i, we add up this is lambda 1 plus lambda 2. That adds up to 8. What is my trace here? It's 8, right? And then the determinant of this matrix is 25. 12 plus 13 is 25. If you were to multiply these together, 4 plus 3i times 4 minus 3i, so this is where the appendix of the book we'll be reviewing how to do all of this, but you basically just FOIL this out. 4 times 4 is 16, then I have minus 12i, and then on the inner term I would have plus 12i, and then the last term is minus 9i squared. But remember that I squared is -1. So this is really plus 9. If you have a 16, these two cancel. Right? 16 plus 9, that is 25. Yeah, so sorry, I should have checked my fun facts to make sure that my lambdas were correct, but they are. They are correct. Okay, now coming back to this, so we've taken this first eigenvalue. We're going to calculate the corresponding eigenvectors by looking at this null space. The first thing we need to remember is that this matrix has to be not invertible, right? Remember, we were setting this determinant equal to 0 over here. So this matrix is not invertible. That means that these two rows, although they may not look like it anymore, they have to be multiples of each other. We have to be able to zero one of them out. if we're gonna trust the theory tells us that this matrix is not invertible. That means if I do the EROs, and please do not do them, but if I was to do the EROs, something would get wiped out. So you know what I'm gonna do? I'm just gonna wipe out a row that I don't want to think about. Okay, so that is going to make your life a lot nicer. We just cross out makers my pivot. And if I want, I can do my thing. So this second row would basically be this equation, x plus the quantity 2 minus 3i times y equals 0. And that's fine. You know, in this case, of course, I would let y equal t. And then if I solve for x, I would get, well, negative of the quantity 2 minus 3i times t. And I could bust out my t from that. I can bust out the t from that and get my basis vector. So my basis for E sub lambda equals 4 plus 3i, my basis would just be the negative of 2 minus 3i and 1. It would just be that. You know what I might do, guys, if you don't mind, I'm gonna go ahead and just get rid of the parentheses here and just distribute that negative so that the answer would actually be negative 2 plus 3i. Okay, so I'm just gonna write it as negative 2 plus 3i. Does anybody remember my my AB trick from Tuesday? I don't know if you guys remember this from the other day. I just want to recall this A-B trick because it turns out that it's quite handy when you have complex numbers to think about. This is the one that said if I have a row with 2 numbers in it and I want to write down an eigenvector, I can get my eigenvector without doing any of this 3 variables business by just swapping. So you swap the positions of the A and the B, and then you put a minus sign on one of them. So here's my A and B right here. What I'm trying to do, guys, is give you an alternative to not having to do this. Okay, so if I just see these numbers A and B here, if I just see these numbers A and B, all I'm going to do is switch the order of them, and I'm going to put a sign change on one of them. I think I'll do the sign change on the first one. So guys, here's how you get the answer without even having to break a sweat. Right, so you just do this A-B trick. You swap the 2 numbers that are in this row right here. So put this one first and then put this one second. And then do a sign change on this one. That's exactly what I have. Some people will ask me, well, can I put the sign change on the other one instead? And that is totally also okay. Because so remember, the way this works is the vector is just negative B and A. Right? You swap the 2 values in that row and change the sign of one of them. People will sometimes ask me, can I put the minus sign on the A instead of the B? And the answer to that, of course, is yes, because after all, if I put the minus sign on the A instead of the B, that's literally just throwing a negative through the vector. And a scalar multiple of a basis vector is just a different basis vector. Totally legit. Totally okay to do that. Okay. Are we okay here? Are there questions about this eigenspace here? Yes, Audrey?
So the eigenvector is the same as the basis for the.
Yeah, this just becomes your basis vector then. The basis consists of eigenvectors. Yeah, absolutely. We have one other eigenspace to do. I just realized I've been talking for a while, so we'll take a break as soon as I get this last eigenvector done. But see, you can see that everybody's going to pull their weight. Everybody's going to pull their weight because everybody has a weight of 1. Okay, there's no repeats here. There's no repeats. So the other eigenvalue is lambda equals 4 minus 3i, right? As annoying as complex numbers are, I do have a little bit of good news for you here. That we don't actually have to do null space again. It turns out you can go straight to the answer. once you are working with this is called the conjugate eigenvalue. You can immediately go to the answer. I'm gonna go to the answer and then I'll explain it. The way you do it, guys, is. So for the basis here, we can go straight to the answer. I don't actually have to calculate anything. What you do to get the answer, so you notice that we already did the answer for the eigenvalue for plus 3i. The difference between 4 plus 3i and 4 minus 3i is just the imaginary part switches to a minus instead of a plus. If you just take your answer here and you change all of the imaginary parts with a sign change, you'll get a correct answer. So I can take -2 plus 3i and change it to -2 minus 3i. So this is just going to be -2 minus 3i. Anything that was real just stays exactly the way it was before. So that would be a 1. So that's the answer. I'm going to put an asterisk there so that I can explain this in your notes for you. So here's the little asterisk comment about this point. It just says that if A has a complex eigenvalue, if A has a complex eigenvalue, lambda equals A plus BI with eigenvector, I'll call it V, which is maybe like R plus SI. This is just to get the formalism of this into your notes. So if I have an eigenvalue with a complex eigenvector, which is what I have here, here's a complex eigenvalue, here's a corresponding complex eigenvector, which you see, you kind of see it right here. Here, the R part would be -2 and 1. And the S part would be 3 and 0. Kind of see if I go across the top of this vector, I see the -2 plus 3i. If I go across the bottom, I see that's basically writing that vector in this form. So if I've done that, if I've written my complex eigenvector as a real and an imaginary part, then here's my punchline. Then lambda bar, I'm going to put a bar on top of this, which just refers to the complex conjugate of lambda. That would be A minus BI. And this is also an eigenvalue. Right, this is also an eigenvalue, and with corresponding eigenvector, now this is going to be kind of annoying. I'm going to write it as B bar vector. So that's a bar on top of the V, and it is a vector. That this is simply the vector R minus SI. Sorry, I kind of caught myself in the corner there. Hopefully that's readable for everybody. But what we're saying here, guys, is that if I have complex eigenvalues, they will always come in pairs. A plus BI and A minus BI, they always come in pairs. And if I simply figure out the eigenvectors for one of them, like we did here, then we can just write down the eigenvectors for the other one by just switching this this sign change right here. This is really the key thing. The real parts don't change. The -2 and the 1 stay the same, but the plus 3i turns into a minus 3i. So that's kind of the point here. So this is a non-defective matrix, right? So we already said that, right? See, it's non-defective. There's no repeated eigenvalues. The reason I did this example was to just talk about what happens when you have complex numbers that show up as the roots of your characteristic equations. Then you're going to be dealing with these imaginary numbers, but things like the AB trick and things like this little asterisk comment here are going to make things actually not so terrible. So shouldn't have to do any real hard EROs with complex numbers. That's gonna be my goal for the next month, is to not have you dealing with that. Okay, well, that was a long section, but we've kind of gone through a lot of chapter 7 now. The only thing I haven't addressed is who cares about this? Like, why do we want to know if our matrix is non-defective or not? Who cares? So I have to address that, but let's take a 10-minute break. During the break, if you need any more problems from the homework to be put up on the board, feel free to do that. And we'll meet back up here at 11:30, okay? Okay. Just for basis, yes. That'd be the best. Thank
That's what I'm gonna. And then for the reasons. I don't know, I barely finished. I didn't. I wish. It was a lot worse than I almost felt messed up because I was trying to. And I was hoping I couldn't get into the down. But it wasn't like they didn't understand. Some things I was a little influenced. But I felt like I'm moving because I was just trying to get through and down. And I didn't have time to do things enough. It's been area. Thank you.
That's why I feel.
And I could say anything.
So.
All right, and we should. So. You think? If you did, I did not know.
The third question was.
Oh, I got that job.
For Kennedy.
The
And.
intern.
Declaration,
I found out.
and then the last question.
Just wait, so.
I
I guess. Feels kind of weird. I feel like I've done something so far and I've been.
Or not February, so it was already like really close to sun.
Yeah.
No, like when I got all seconds, it started.
Yeah, cause it's weird where I'm like, I'm literally, this is like half a year away. I don't know, how do you work?
No, I later learned talking to other interns that most applications open in November. I just slipped through the cracks because I was like, I need different parts.
See, that's what I, last semester, I made that mistake when I thought, oh, I have time.
Yeah.
Like, what do you mean, it's only what, month? And then I was like, oh, and I'm like, oh, you're not gonna make that mistake next time.
I mean, some things still open in spring, like I said. I
It's all
applied,
about that because it's like the last thing.
yeah, I applied in February, got the job I do.
Do you know what that? Well, it's hard because you're mechanical. What is like the average?
I got no idea.
Trying to get a feel of it, yeah, trying to get a feel of it, but you're the only person who I know what they. Like, wonder.
So you have very small data.
Yeah, and I think Indeed is giving me like. Like Indeed go through all of that. Yeah, like I'm trying to gauge what's like an average. What's on the high end of the list.
Oh wait, I was gonna say.
I'm still.
I was gonna say. But like,
Okay.
that's also public health. Like that is so.
Oh, it's not engineering.
I'm just talking about like, from my brain, like the
Yeah.
stuff, all the internships I made, and I talked to more than just engineering.
Yeah, I was just curious.
Granted, I took the civil too, so.
Cause you know, you look on Indeed, but I'm accurate, they like.
If you really wanted, and this was thought, like, you could just look up what came in, like, spreadsheet.
There was like, yeah.
What do you mean? Like look on the. code.
Yeah,
But they don't post the code.
sometimes they do.
It's the-
The multiple choice.
Yeah.
The multiple choice multiple choice.
Not that I really care, it's just like curious, you know, to see or what. It is. But,
I mean, it's like, that's true, negotiating, so I'm not ready enough to talk about.
I mean,
We'll add minus.
happy to know for like. Like this size.
Well, if you want to go back next summer, you could definitely, if they don't already give you a raise for coming back. They always negotiate like, hey,
It's like.
Yeah,
I was
cause
here last
I didn't know if it was on like, I think it's on like good end, but I didn't know whether it was like. Cause you said with five, and then I was like.
I think that's really high.
Yeah, cause I was expecting something high, so then I was like,
I heard that.
okay, should I be making sure that I'm not getting like.
Mobile.
Yeah, cause I don't know,
You should have seen it first, everything.
it's not that deep, I mean, it's a good pay. It's a good pay for me, so I'm happy.
It's the resume. and those-
Yeah, I'm more focused on the job than I am the pay, but I just don't need to be.
Yeah. The rest is-
Are you?
Yes, well, so I wanted to say that. Is my same as also.
That's how I took it, I didn't know if I was gonna, I interviewed the second interview, and I was like, I don't know if I'm gonna guess with me. Like, I'm just gonna feel like, well, I didn't feel like, I don't know, I wasn't feeling like very confident. You know, so it was like maybe I'm gonna have to like find like a million of internships and cover that, you know, and it's like.
I should start.
Because they're gonna.
Like,
That's how because I haven't done it, and I was thinking, if I don't get this, like, I'm gonna have to like push out this week. Like, if you're gonna do it or try to like push out this week, and then next week we'll need this. Cause most of them are already in the rooms. And it's like, you're half a year away.
What's stopping you from backing out? So I kind of need to plan ahead. So that was backing out. They have more chances.
But realistically, I thought that I was but that's how all the engineering internships are so clean. So that they don't receive no. The exact age and you're really concerned, really, it's like, yeah. No, don't be scared, you still have time, it's not like it was like a month before and everything. So I would-
Oh my god, like I should start applying like no, it's late, like.
Yeah,
Like,
well, I applied it last semester and I didn't hear it because like, I mean, maybe I was probably, but I also feel like maybe it was like, I just applied to it, I didn't know. I had nobody telling me, you, I haven't even been saying about it, I didn't have any telling me.
meaning.
So I figured it out though, before it went.
Lucky, unlucky, because my internship was even engineering. I'm so good at it anyway.
We just have something to put down.
Like I got to watch and talk to engineers.
Yeah, I'm doing it.
I was actually doing an EH.
So what engineering?
Yeah, but it was public health and engineering.
Okay.
So you get exposure to engineering.
You don't think you'd wanna try to reach out to the same company and do engineering part of that?
No, I'm not going to.
Yeah,
Like, it's not. Like, this is what's out there.
Like, do you have connections there?
Well, definitely not like,
Yeah. Can you like reach out to your whoever was in charge of you or something, and be like, hey.
I'm meeting with.
Oh, from that company? Oh, then I would hit up and be like.
Well, sure, guys, I think maybe I'll go ahead and, yeah, the rest of my action here. We only have 20 minutes, so that's just gonna be kind of short. A short little bit here at the end of class, but I'm mostly gonna do here the last part of today. We kind of covered a good amount of chapter 7. Now, so I want to go back and try to help you a little bit with the homework that's due tomorrow night. Don't forget, you have till tomorrow night. I'm gonna send out an email with some extra office hours for tomorrow. And I realize some of you have maybe not had a chance to like go into all some set of problems yet. But that's okay. You can follow along and take some notes on it, and of course study it a little bit more as you're getting ready to submit your assignment. But I think these are some nice practice problems going back into chapter 6 again. I'm actually going to start with number 43 over here, which is actually one of my favorite problems that I assign in the entire semester. And I've actually been known to put this on my exam before. So this is definitely one you will want to understand how this works. What I like about it is that you can see that it has it's a proof, so it's a theoretical exercise, but it involves the concept of one-to-one as well as linear independence. So something from chapter 4 and something from chapter 6 kind of blending together here. So what does it say? It's asking us to prove that if T is one-to-one, can somebody remind me, what does one-to-one mean again? Kernel equals 0. Yes, exactly. So I'll go ahead and remind everybody of that here. The kernel is 0. Right. So if T has a kernel of 0, and if we start with some vectors that are Li, and then we transform all of those vectors, then what we're going to try to convince ourselves is that the resulting vectors are still Li. Now, that's not normally guaranteed to be true. If the kernel was not 0, then you could have a beautiful set of linearly independent vectors that somehow become linearly dependent after you transform them. But as long as the kernel is 0, we're hoping to prove that linear independence is sort of respected by a linear transformation. Okay, so that's what we're going to do here. So this is actually what we want to prove here. I'm gonna grab the bull by the horns and really try to focus on what it is I want to show. I want to show that these vectors, T of V1, T of V2, and so on, that they are Li. Does anybody remember the definition of Li, like how I would set that up?
In a linear combination, it would go from equal 0 all the way to coefficient.
Okay, yeah, so in case anybody couldn't hear that, the definition of Li is that if you have a linear combination of your vectors that cancels out to 0, the only way that could have happened with that linear combination is if all of the scalars of that linear combination had been 0 to begin with. So let's see if we can prove that that's true here. So this is going to be my solution. I'm going to assume that C1 times T of V1 plus C2 times T of V2 plus ... plus CK times T of VK is equal to 0. I'm going to take a linear combination of the vectors over here. Okay, I'm not going to try to force the assumptions into the solution yet. I just want to set myself up for success. I write down a linear combination of the vectors that I'm trying to prove. And what do I want to show right now? As I just explained it, for linear independence, what do I need to show? All the C's are 0. Exactly. We will show that C1 is equal to C2 is equal to ... is equal to CK is equal to 0. That's what I need to show. I'll put that kind of in parentheses. That's not really part of my proof. I just want to get it in your thinking as to that's where we're headed. Okay, so this is my starting point. Starting point is right here. Anybody have a suggestion what I could do with that box equation? Blake?
Using the property of linear transformation condition, you could factor out all the transformations, so C1, C2.
I like everything you said, except I'm gonna say I would like to factor it in, not out. It's actually already factored out, right? The constants are on the outside. So if you remember, guys, a linear transformation respects addition and scalar multiplication. So what I can do is I can come into that box and I can put everything on the inside. I think this is exactly what Blake was getting at. But in this case, everything starts on the outside and we're just gonna move it all to the inside. We're gonna move it all to the inside. So this is just what it means for T to be linear. It respects this linear combination. Okay, so now what am I looking at? T of this whole thing is equal to 0. What does that tell you about the thing that you've plugged into T? If you transform it and it becomes 0, what does that say about that vector that you plugged in? It's in the kernel. Right? Remember, what is the kernel of T? It's those vectors that get transformed to 0. That's the definition of the kernel. Well, here I have a vector that's being transformed to 0. Okay, so thus, the vector, which is C1v1 plus C2v2 plus ... plus CK_vk, that vector lives in the kernel of T. It lives in the kernel of T, absolutely right. Okay. But what is the kernel of T in this problem? We got that right here, right? It is 0. So this must actually be 0. Okay, so I need a little more room. I saved myself just enough room. I'm gonna come way over here. I'm just gonna write this down. So since T is 1 to 1, the kernel of T is 0. So C1v1 plus C2v2 plus ... plus CK_vk must be that 0 vector. That's the only vector in the kernel. And so that has to be the 0 vector. Again, let's not lose sight of what we're trying to do. We're trying to show that the C's themselves are 0. What I have right now is a linear combination of V1 through Vk that cancels out to 0. Do we know anything about the original V1 through Vk? The original, so you're gonna use everything that's written here, right? So we haven't talked about this yet. The original vectors are Li, which means that if I ever see those original vectors in the linear combination canceling out, then the constants in front of them have to be 0, right? So let's just say since the set V1, comma, V2, comma, ... comma, Vk is Li, we get that C1 and C2 and ... up to CK, they are all 0, and that is exactly what we were hoping to end up with. That is the punchline. All of the constants are 0. So you see, it's because the kernel is 0 that somehow, see, at this point, the T is gone. There is no more transformation in my equation. It's just a combination of the original vectors. And so that's when we go back and use the fact that the original vectors are Li. I love this problem because it's a good reminder about what linear independence means as a definition, and a good reminder about how 1 to 1 works, right? The kernel is 0. So it's 5, 6 lines, something like that, but each step by itself is pretty much just a baby step using either the definitions or some simple property about the linear transformation T. Does this make sense? Jason? That's the most common sort of flaw that people will run into, is they'll start from here and kind of It's because the definition of linear independence is so slippery that people will sometimes sort of, like, they'll say, oh, the original vectors are Li, therefore we know this is true. And that actually is not what Li means. Li means that if this is true, then the constants are zero. So it doesn't mean that literally this thing that I circled is automatically true as the assumption. And that's where the slippery nature of Li can get people into a little bit of trouble. So you really need to do it in this order, focusing on what you're trying to prove here, rather than just forcing this into the proof from the beginning. You actually end up putting this into the proof, not till the very end, actually. That's a great point. Okay, having done that, let's take a look here at number 12 real quickly. I'm going to do this really quick because I want to make sure I save a little bit of time to do the ones from 7.1. Here's a matrix transformation, right? What's the size of this matrix? 2 by 2. So T would go, in this problem, T goes from what to what? What's the V and what's the W? It's R2. It's always Rn to Rm. In this case, the N and the M are both 2. It's a 2 by 2 matrix, so that should be R2 to R2. And they gave us the matrix. And they actually asked you to find the kernel and the range of this transformation. I'll just remind you here that the kernel of T is just the null space of the matrix. And the range of T, so we talked about this quite a bit. The range of T is always just the column space of the matrix. And if I want to figure out what those things are, well, for both of these, I just need to do the EROs here, right? So just take the matrix, do the EROs, you have a 1 and a 2, cancels out that bottom row. Okay. And so you get your pivots, your one pivot right here. And so for the null space, I'm just going to give a basis for each of these. So we'll do a quick basis here. The basis on the case of the null space, guys, we can use my little, let's use that little AB trick now. Instead, we can set up a free variable and do all that if we want to, but we don't really need to. I'll just swap those two numbers and put in a minus sign on one of them. I'll put the minus on the 2. So we'd have a -2 and a 1. That would be my basis vector. That's the only basis vector because I only have one free variable. So we can actually just do that almost at a glance. If you don't like that, of course, you can go back as we've always been doing and write in the equation and set y equal to t, and then x will be -2t. Bust the t out, you'll get the same basis vector. Okay. What's my basis for my column space going to be? Yep, we just go back to the original columns of A and we take the pivoted columns that correspond to what we came up with in the row echelon form. So it's just the vector 1 and -2. Okay. And they're going to ask us whether this is 1-to-1 onto both or neither. Since V and W are the same size, you probably remember it has to be both or neither. Oops, I crossed the wrong thing. No, I didn't. I did good. It's either both or neither. And that's because the dimensions are the same. So it's both or neither. And how do I decide that? I really have 2 ways I could do it right now. One way would be to just say, well, look, the kernel is not 0, right? And the range is not all of R2. So this is definitely going to be neither. And I could also figure it out just from the determinant of this matrix. You might remember, if it's a square matrix, you can take the determinant of it, and the determinant here will be 0. That's bad. Right? When you get a determinant of 0, we generally think of that as a bad thing. And that would also suggest that the answer should be neither. Okay. Any questions on number 12 there? Okay, let's come over here then. Number 15. Actually, the same kind of problem. I maybe won't go through all of it right now, but I can tell you that, out of these four choices, one to one, onto, both, or neither, can we cross off two answers that we know are not correct, just right off the top? Definitely can't be both. See, the V and the W are not the same size, right? In fact, V is bigger than W, so do you remember yet from that? You will definitely learn this, I know eventually. So do we know it by now? Actually, the other way around. If V is bigger than W, then it can't actually be one to one. Okay, so those bullet point facts that we wrote down last couple of classes, that's where you'll find that summary. And just based on that alone, see, I haven't even looked at T yet, other than V and W, right? Just based on that, I can figure this much out already. And then there will be a matrix for this because it goes from Rn to Rm, and it will be a 2x3 matrix. And I'm just going to remind everybody how you make this matrix. The way you make this matrix is you take the standard basis vectors and lay them out column by column by column. So T of 1, 0, 0 is 4, 5. That goes in the first column. And then T of 0, 1, 0, that's negative 1 and 1. That goes in the middle column. And then, unfortunately, the third column would have been T of 0, 0, 1, which they did not give us. So you actually have to figure out what that is. I'm going to let you do that. You have to figure out what that third column is. But I can tell you that I've done enough work here already, even without knowing what that is, to know that if I did my EROs right now, I would get pivots that look like that. That would be 2 pivots. And that would mean that my column space would be 2-dimensional, which matches W. The range of T will be equal to W. This one is going to be onto. So I can figure that out already, even if I didn't fully work out the whole matrix here. So can do that one pretty quickly. I don't even think they're, well, they do ask you to find the matrix of T. So the one thing I didn't do is these little question marks. I'm gonna let you guys work on that part. You can always ask me later if you can't come up with that, but that's basically the idea there. Yep, I got 2 pivots here. That means that the dimension of the column space will be 2. And that is the same as the range. So if the range is 2-dimensional, it matches W. It matches W. Yeah. Number 20, this one, well, I pretty much put it on the board already. B is the set of 2x2 symmetric matrices. And T is a transformation that goes from V and goes to P2 of R. And this is the formula. Take note here on this 2x2 matrix. This is not A, B, C, D. I wrote it as A, B, B, C. That's because if the matrix is symmetric, these 2 entries have to agree. They have to agree, right? So that's the point there. And they're just asking if T is 1-to-1 onto both or neither again. Can somebody tell me what's the dimension of V here? It's easy to get tripped up because it says 2x2 matrices, so you think, oh, that's M2 of R, which would have been 4-dimensional. But because the matrices have to be symmetric, as you can see, there's only going to be 3 variables to bust out. If you were going to like sort out a basis here, this would be your vector. If you bust out the variables, you would only get 3 matrices out of that. And notice that that is also the same as the dimension of W. So W is P2 of R. That's my W, and we hopefully know that the dimension of that is also 3. So if the dimensions agree, then which are my possible right answers? It's got to be both or neither, so I'll cross off those 2. It's got to be both or neither again. And this time we don't have a matrix. Let's just be clear, this is not a transformation from Rn to Rm. So I can't use a matrix approach. I have to go back to kind of what does it mean, you know, for the, what does one-to-one mean, for example? Well, it has to do with the kernel. Or I can focus on onto, which has to do with the range. I think I'll just do the kernel for a moment. Remember that for the kernel, if I want to solve for the kernel of a t, I would be setting the transformation equal to 0. And then solving for the inputs. When I set this equal to 0 here, guys, it's very important that you understand that that's not the number 0, that's the polynomial 0. So you could think of it as 0x squared plus 0x plus 0. And what are you going to conclude from that? A, B, and C, they're all going to be what? Just 0, exactly. And if they're all just 0, then my kernel, right? What is my kernel matrix here? If I look at this matrix and I'm putting all zeros in there, well, that's your kernel. It's just 0. So that means that the kernel is 0. In other words, t is 1-to-1. Right? T is 1-to-1. Well, if it's 1-to-1, then it's got to be both. Because they go at this point, it's either both or neither. If it is 1-to-1, then it's going to be both. So what I wanted to address, I know I've got like -1 minute left, but I'm just going to very quickly tell you, if they ask a follow-up here, they say find T inverse. And I have not really talked about this. So you can kind of assume I'm not going to make a big deal about it. But all that this means is that you can, first of all, you can only find T inverse if it's both. Otherwise, there is no T inverse function. And the way it works, guys, the T inverse is literally just turning the transformation T around. Basically, the outputs turn into the inputs and the inputs turn into the outputs. This is what an inverse does. So the answer to this is actually easy. All you have to do is write down T inverse of, so now you're going to plug in the polynomial. So the outputs now become the inputs. So I plug in a polynomial and I'm going to output a 2x2 matrix, A, B, and B and C, just like that. And so that's it. You don't have to show any work. You basically just take what was given here and you just swap the positions. It's a function that literally just turns all of the arrows around and they go back the other way. Guys, how would you feel if I make a little video to explain the 7.1 problems that are over there? Would that be good? Let me just do that. Number 9 and number 42B. I'll make a video. I'm going to send you an email probably by tonight that has some extra office hours for tomorrow and a video with the solutions to be listed. Fair enough? All right, guys, have a great rest of your day. Hopefully you can survive with all the sinus action with all the dust.